We know that with a geometric sequence, we begin with a term and we multiply by a common ratio to get each new next term in that sequence until we get to the final term in that sequence, the general term. If we have a geometric series, we're replacing each of those commas in the sequence with a plus sign, where we can then add all of them up to determine the sum of that series. So let's take a look at where this formula comes from. We're going to use a more formal mathematical approach to derive this formula, as opposed to the inductive reasoning we used with arithmetic. So if we're looking for the sum of a geometric series, I'm just going to begin by listing all of the terms that we're going to add up until we get to that very last term. Now, if we go back one term, so the second last term in that particular series is going to be term 1 times 2 less common ratios than this term that we happen to be on. So this last term is 1 less common ratio than the term we're on. This second last term is 2 less common ratios than the term that we happen to start with. I'm going to take that entire geometric series and I'm going to multiply the entire thing by a negative r. So when we do that, we're going to have negative r times s sub n is going to give us just negative r s sub n. Negative r times term 1 is going to give us a negative term 1 r. I just kind of put the negative out front. We're now going to have a negative r times term 1 r. So we're going to have a negative term 1, and now r times r, we're adding the exponents. We're going to have r squared. And then we're going to keep going all the way along here. And then when we get down here, we're going to have a negative times term 1 is a negative term 1. And then r times r to the power of n minus 2. Now I can even go up here and show you. When we multiply powers with the same base, remember we're adding the exponents. So I've got 1n, that 1n stays the same. 1 minus 2 is negative 1. So when I multiply negative r times this term, we end up with negative term 1 times r to the power of n minus 1. And then our last term, negative r times this term, is going to give me that negative term 1. And again, this is a 1 on that r. So I'm going to have n, and then negative 1 plus 1 is 0. So we end up with an exponent of just r to the power of n on that last term. And then if you take a look at this, you're going to notice we have a lot of pairs of terms throughout this series. So we have term 1r, we have a term 1r, we have a term 1r squared, we have a term 1r squared. We have a term 1r to the power of n minus 1 and a term 1r to the power of n minus 1. So we can create a system out of these, and if I add those two together, we're going to end up eliminating a lot of those pairs. So we're going to have s sub n plus negative r times s sub n. So we're just going to have that piece there. And then you're going to notice a lot of these pairs will cancel. So term 1r plus negative term 1r, those are going to zero out. And then we've got term 1r squared, and we have a negative term 1r squared. Everything in here in the middle is going to end up canceling out as we move along here until we get to this very last term is going to cancel with this term down here. So the only terms that do not cancel are that original term 1 here, so that's going to show up in our final sum, and then this last term down here is also going to show up. So what we can do now is say, okay, we have an s sub n and an s sub n. I can factor one of those out of here, and we have a term 1 and we have a term 1. So I can factor 1 out of this piece over here. And because we're ultimately trying to isolate the sum of those terms, I can get rid of this 1 minus r by dividing it out, and then that's going to cancel on the left side, and then we're going to divide it out on the right side. And this is one formula that we can use to find the sum of a series if r is a proper fraction. So for example, if r is 1/2, 1 minus 1/2 is a positive 1/2. This format allows us to avoid getting negatives in the denominator. We can also rearrange this. So let's say r is a whole number, such as 3. 1 minus 3 is negative 2. We would then have to move the negative up. So we can just quickly rearrange the formula right now. So I just rewrote each bracket with the terms in a different order. So I put this negative r to the power of n first, and then this plus 1 second, and then negative r put first, and then this 1 I put second. And then I'm going to factor a negative 1 out of each bracket. So I'm going to put a negative out here, and then remember we're flipping every sign in the bracket. So if we were to redistribute that in, we'd have a negative r to the power of n, and we would have a positive 1, which is what we originally had. So we didn't change the question. And then I did the same thing here. I factored a negative 1 out of that bracket on the denominator, and then a negative divided by a negative becomes a positive, so we're left with this. So either formula will get us the sum of a geometric series. To use either of these formulas, we need to know the first term, the common ratio, and the number of terms. If we happen to know the last term in that series, we can also use this formula. We know that the general term in a geometric sequence is just term 1 times the number of common ratios that we happen to have. It's always 1 less than the term that we're on. So if I replace t sub n with what it's equal to, then we can just algebraically rearrange this here. So what we're going to do is multiply this r into the bracket. So we have an exponent right now of 1 on that r. When I'm multiplying powers with the same base, we've got an r to the power of 1 and we've got an r to the power of n minus 1. We're adding the exponents. So we're going to have n and then 1 plus negative 1, that is going to be 0. So we're just left with that r to the power of n. And then we can factor a term 1 out of the numerator. And when we do that, we end up with the formula that we just derived. So this piece here, you can see, is going to be equivalent to this. In each of these formulas, r cannot equal 1. If we put a 1 in for r in the denominator, that will give us a denominator of 0, which makes that undefined.